So now we want to find the equation of the line parallel to PQ. Now that's the same PQ from the last two examples, right, which was in example 4 and 5, but it contains this new point for -1, which is R. So I've drawn the line again, so that's PQ, and then we have point R right here. Now if you think about this, we had two direction vectors pointing in opposite directions of each other, right, but along that same line. So we have one kind of pointing that way, kind of downward, and we have one pointing back, right? So this particular one was pointing downward, the 3, -2, and that one was pointing upward. All right, so we could write the equation of this line using either one, right? So let's use direction vector. V is equal to 3, -2. Okay, so that points that way, 3, -2. So if we do that, it'll come off of R like that and be parallel to the line. Okay, so let's think about this. We want R of t is the direction vector times t plus OR in this case because R is our point. So it'll be 3, -2 times t plus, and then we're going to vectorize, for lack of a better term, 4, -1. Since it's coming from the origin, it will just be those same numbers but in vector form. So now if we want to write that in our more standard way, 3t plus 4, -2t minus 1. All right, now I could also write it using the other one, right? So I could use the direction that went the other direction, which was, let's think, -3, 2, which was pointing up the line. So if we did that, it would kind of come this way. Okay, so then R of t would be equal to -3, 2 times t plus 4, -1, which would be -3t plus 4, 2t take away 1. Now if you're thinking to yourself, well, which one of these is correct? The answer is both of them are. They are both vectors that are parallel to that line, right? And because they're in vector value form, they find the equation of that line. So it works either way. Now, everything we've done so far has been in 2 dimensions. What if we kick it up a notch to 3 dimensions? Well, 1, it's going to become a lot harder to draw, but 2, other than that, everything else should work pretty much like we expect. So we're going to find an equation for the line AB, given that A is that, oh, this must be a typo, B is that. We're going to make that B. Sketch the graph of the line and also find and sketch the projection of the line in the XZ plane. Okay. So of course the first thing we want to do to find the vector equation will be to find the direction vector. So that's the first thing we need. We need a direction. And the direction will, you could do it either way, A to B or B to A. It doesn't really make any difference, as we saw in the previous problem. So AB would be, we're going to take terminal minus initial. So 3 take away 6, 3 take away -1, and 1 take away 4. So that's -3, +4, -3. All right, so that's our direction vector, V. All right, and then OB would be to vectorize 3, 3, 1. Or if you like, you could do OA. It doesn't really make any difference, right? So because vectors are free, you know this is the direction. So you could use OA, and that would be 6, -1, 4, either one, right? So R of t would be equal to, And of course, because we're trying to do a line, you could actually do BA as well. So it gets complicated. There's always like four ways you could do these problems. So I'm just going to pick one. I tend to stick, just me personally, I tend to do OA and then A to B. It's just the way my brain thinks, but you could do it any way you like. So direction would be -3, 4, -3 times t plus, and then I'll do 6, -1, 4. Which, of course, this is perfectly fine to write it that way, but it's not the most common way we write it. So -3t plus 6, 4t minus 1, -3t plus 4. All right, so either one of those is fine. And again, it's not the only way you could do it. You could use that direction with the other point, or you could go the other direction and then use either of those points. There's always 4 ways to do these. So you just pick one, right? Because it's not specifying which one you have to do. So they all would work. Now the bigger issue is going to be to try to draw this thing and then find and sketch the projection of this thing. Okay, so to draw this thing, let's start. 6 out here. So 1, 2, 3, 4, 5, 6 in the x direction. -1 in the y direction. And then up 1, 2, 3, 4. So A is kind of over here. And I could draw a box to get there, but I don't want to do it because it's going to clutter everything up. That's the problem with drawing in 2 dimensions. So you're just going to have to trust me that it's in that particular octave. All right, B is out 1, 2, 3, over 1, 2, 3, and up 1. So it's right about there. And then there's our line. Now, the problem is we have no perspective on this, so everything's just kind of floating. You don't really know where anything is. And so there's an XY plane below this, and there's a shadow cast onto the XY plane by that vector, or by this line, I should say, and the vector that includes the line. And so that's why it's saying find and sketch the projection of the line in the XY plane. All right, well, we're just going to kind of wave our hands at this a little bit. Let's think about this for a second in Maple. If we take our graph, right, there's our line, and if I cast its shadow down so you can see, that right there is the projection, right? So what's happening? Well, it doesn't have a z component because it's in the xy plane. That's what the shadow would have. It would have the same up and right or down and left, right? The x and y components of the vector would be the same as they were in the original, but it wouldn't have the z component. And the easiest way to do that is just to turn the z component into 0. So if I do that, let's look, which I already did. So here it is. So if I put the z component as 0 and I leave the x and y the same, you can see that that red line is sitting on the xy plane, but it's actually the shadow that the blue line would cast if it was down. So that's the projection of the blue line onto that xy plane. Would have the same x and y components as our vector valued function for the blue one, but it's turned the z component, which is how it gets its tilt from the horizontal, to 0. And if you do that, it just pivots the blue line and makes it flat on the xy plane like the red line. Great. So that means that the shadow it's casting, let me grab a red line. Let me grab a red pen here. The shadow it's casting is on the xy plane. So let's look at that actually one more time. Okay. So if we look at that shadow, it's going from negative, just a little bit above or below -5. Oh, I actually have my axes in the wrong place. That's positive. That's negative. Sorry, I'm in the wrong position. Hold on. There we go. There's other ways to tilt this, but this is easiest. Okay, so there we have it. So it's going through y is 7, and then x is 5. So y is 7, and I'm going to put those dots on my paper I'll be right back to the paper. There we go. So there we go, 7 and 5. So the shadow it's casting is actually here, but that's hard to see from the 3 dimensions. This is why we draw in Maple rather than doing it by hand. Oh, and I just thought you'll notice that they actually touch. It looks like right around over 2 up 5 or over 2 up 4, somewhere in there. They're touching. And so it's coming across and hitting over. So the blue part on the low side is actually below. So if you tilt it so that it looks like how it looks on the page 3-dimensionally, it looks like that, right? So that piece is coming towards us. So that's the red piece that we're seeing right there, right? So drawing in 3 dimensions is weird, I know. So the projection of R of t onto the xy plane would be -3t plus 6, 4t take away 1, 0. And we've learned that we very much want to draw these things in Maple rather than on paper because they're really hard to grasp what you're looking at on paper, whereas you can swing things around in a computer program.